Hi, we are yet to begin our discussion on electromagnetic waves. We have so far been discussing about mechanical waves, and in the previous section, we have discussed about the mathematical formulation of mechanical waves. In this lecture, we shall embark on yet another aspect of mechanical waves, its reflection and transmission at discontinuities. In the previous discussion, to formulate the mathematical equation for wave motion, we have been considering a string that has been extended to plus and minus infinity. That is, we have been considering an infinitely long string. And in that case, we need not worry about what happens to a wave when it reaches the end. That situation changes when we have a string that is attached. This is equivalent to a change in the medium, and we have to find out how the propagation be affected if the string is attached at one end. To bring home the point of discontinuity in the media, let us consider this example of two strings having two different mass per unit lengths attached at point z equal to 0. In this example, this direction will be taken as plus z and this direction will be taken as minus z. And the strings are simply tied to one another at the coordinate position z equal to 0. The tension T is the same for both, but the mass per unit length mu is different in the two cases. Because the mass per unit length is different in the two cases, the velocities at one section will be different. Let us take v1 as the velocity of the string that is there on the left and v2 as the velocity of the string that is there on the right. The velocities on the two media, that is the lighter string and the heavier string that is shown in the figure, will be different as velocity is equal to square root of tension divided by mass per unit length. You might have noticed that the incident wave on the string is a pulse. This is because truly sinusoidal waves are hard to transmit in a string. Therefore, we can consider pulses as propagating through the string, and we know that mathematically pulses are built up as a linear combination of true sinusoidal functions having a whole range of frequencies and wavelengths. As shown in this figure, a single pulse can be considered to be a combination of a number of frequencies. In case if we want to transmit a single frequency through the string, we can consider a pulse that is extended to infinity. That is, we will use a very long pulse. Now, let us consider the incident pulse is having the mathematical form complex f, which is a function of z and t. This is equal to the complex incident amplitude e raised to k1 z minus omega t. In the coordinate system, the point where the two strings are attached will be taken as z equal to 0, and the direction towards the right will be taken as positive z, and the direction to the left is negative z. So this wave represents the complex incident wave fzt. We shall take this as equation number 12. And this is for region z less than 0. Now, as the wave encounters a change in medium, or as the wave hits at z equal to 0, reflected and transmitted waves arise. The reflected wave propagates to the negative z direction with a velocity v1, and the transmitted wave propagates along the positive z direction with a velocity v2. We shall write the equation for the reflected wave as Fr, which is a function of z and t. This is equal to the complex amplitude AR, then e raised to I, negative of k1z minus omega t. So this is the region z less than 0. And for the transmitted wave, we can write Ft, which is a function of z and t. This is equal to complex amplitude At, then e raised to I, k2z minus omega t. So this is for the region z greater than 0. We shall take this equation as 13 and this one as 14. For this discussion, we assume that the incident wave Fi is a sinusoidal oscillation that extends, in principle, all the way back to z equal to negative infinity. This is the same for Fr, which extends up to negative infinity, and we can see that Ft extends up to positive infinity. We also assume that all parts of the system are oscillating at the same frequency omega. Since the wave velocities are different in the two strings, the wavelengths and the wave numbers will also be different. The ratio of the wavelengths lambda 1 over lambda 2. So in terms of the wave number, this is 2 pi over k1 divided by 2 pi over k2, and this is equal to k2 over k1. In terms of the velocities, we can write the wave number as omega over v2 and omega over v1. Therefore, this will be equal to v1 over v2. For a sinusoidal incident wave, the net disturbance on the string will be a linear combination of incident and reflected waves for z less than 0 and only the transmitted wave for z greater than 0. So this can be mathematically written as complex f zt equal to ai e raised to I k1 z minus omega t plus complex AR e raised to I negative k1 z minus omega t. So this is a case when z less than 0, and for z greater than 0 we can write at e raised to I k2 z minus omega t. We'll represent this as equation number 15. If the wave is to propagate from one media to another, the complex wave function f zt has to be continuous at z equal to 0. Mathematically, this can be represented as f complex 0 minus t equal to f complex 0 plus t, where 0 minus represents an infinitesimally small displacement to the left of z equal to 0 and 0 plus represents an infinitesimally small displacement to the right. And if the knot itself is of negligible mass, then the derivative of f must also be continuous at z equal to 0. This can be mathematically represented as partial of f over partial of z at 0 minus equal to partial of f over partial of z at 0 plus. To further understand the meaning of this equation, let us consider a graphical representation of the knot at z equal to 0. In the first case, there is a discontinuous slope, that is, partial f over z at 0 minus is not equal to partial of f over partial of z at 0 plus. From this representation, we can see that the slope at 0 minus is not equal to the slope at 0 plus. The discontinuous slope would indicate that there be a net force on the knot and therefore an infinite acceleration. Whereas in the second figure, you can see that the slope is continuous and there will be no net force on the knot. We shall now substitute equation 15 in equation 16 to determine the outgoing amplitudes, that is AR and AT, in terms of the incoming one, that is AI. When we do that, we'll get AI I K1 e raised to I K1 Z minus omega t plus complex A R negative of I K1 e raised to I negative K1 Z minus omega t. So this is defined for the region Z equal to 0 minus, and this will be equal to AT IK2 e raised to I K2 Z minus omega t, which is defined at Z equal to 0 plus. From this equation, we have AI K1 e raised to negative I omega t minus AR K2 e raised to minus I omega t. This is equal to AT K2 e raised to minus I omega t. All the e raised to I omega t gets cancelled, resulting in K1 AI minus AR equal to K2 AT. We also have this equation, the incident amplitude plus reflected amplitude equal to the transmitted amplitude. In the next step, we shall add equation 17 and 18. So this gives us 2AI equal to AT times 1 plus K2 over K1, that is AI equal to K1 plus K2 over 2K1 times AT. We'll revert this equation so that AT equal to 2K1 over K1 plus K2 AI. So this is the transmitted amplitude in terms of the incident amplitude. We'll now add equation number 19 and 18, which will give us AI plus AR equal to 2K1 over K1 plus K2 multiplied by AI. From this, 1 minus 2K1 over k1 plus k2, ai equal to negative of ar. As we write ar in terms of ai, we have ar equal to k1 minus k2 divided by k1 plus k2 multiplied by ai. Now in terms of the velocities, at equal to 2 multiplied by omega by v1 divided by omega over v1 plus omega over v2 multiplied by ai, and this is equal to 2 over v1 divided by 1 over v1 plus 1 over v2 multiplied by ai, and this is equal to 2 over v1 then v1 multiplied by v2 divided by v1 plus v2 multiplied by ai, and from this equation we have at equal to 2 v2 divided by v2 plus v1 multiplied by ai. In a similar manner, we can write the expression for ar as v2 minus v1 divided by v2 plus v1 multiplied by ai. We shall take this as equation number 21 and 22. How would the real amplitudes and phases be related? They are related as ar e raised to I delta r. So this is what we call as a complex r, and this is equal to v2 minus v1 over v2 plus v1 then ai e raised to I delta I, and this is what ai is. Similarly, at e raised to I delta t, this is equal to 2 times v2 over v2 plus v1 multiplied by ai e raised to I delta I. We'll now consider 3 cases. In the first case, the second string is assumed to be lighter than the first, so that mu2 is less than mu1 and therefore v2 greater than v1. In this case, all the 3 waves will be having the same phase angle, that is delta r equal to delta t equal to delta I, and therefore the outgoing amplitudes are ar equal to v2 minus v1 over v2 plus v1 multiplied by ai, and at is given by 2 times v2 over v2 plus v1 multiplied by ai. If the second string is heavier than the first one, that is mu2 greater than mu1, the velocity of the waves that are propagating in the second string will be less than that in the first string. In this case, the reflected waves will be out of phase by 180 degree. And the phases are related by delta r plus pi equal to delta t, and that is again equal to delta I. In this case, the reflected wave will be upside down like this. That means that there is a phase difference of 180 degree upon reflection at z equal to 0. Mathematically, we have cos of minus k1 z minus omega t plus delta for the reflected wave, and this is equal to cos of negative of k1 z minus omega t plus delta I minus pi. So this is delta r, and this is again equal to negative of cos k1 z minus omega t plus delta I. The corresponding amplitudes are AR equal to V1 minus V2 divided by V2 plus V1 multiplied by AI, and AT equal to 2 times V2 divided by V2 plus V1 times AI. Now the third case. In this case, we assume that the second string is infinitely massive. In this case, there will be no transmitted wave, and AR will be equal to AI, and then AT will be equal to 0.